Okay, so how do you even start to make sense of just the sheer amount of information that hits you every day? I mean, how do you get to the real insights, the important stuff quickly and, in a way that actually sticks?
Well, that's what we try to do here on the deep dive. Think of it as your shortcut to getting properly informed without all the usual overwhelm. Today, we're diving into something that's, well, it's really old, but also super modern at the same time. Linear regression. It's this fundamental tool. You see it everywhere, but it's also getting this massive boost from machine learning and AI right now. It's fascinating.
Yeah, it really is. So our mission today, if you like, is to unpack predictive inference using linear regression. We want to look at its strengths, its weaknesses too, especially now with, big data, and then crucially see how it actually helps us understand real-world things like wage gaps. And we're basing this on a great resource, CausalML-trap1.pdf. It's by Ternozikov, Hansen, Callis, Spindler, and Serkanis, the March 5th, 2025 version. What blows my mind is that the basic idea, least squares, it was introduced back in the early 1800s, Legendre and Gauss. So we're talking centuries here. This tool has been fundamental for ages. So, okay, it's old, sounds simple, maybe a straight line. But as you're going to find out, there's a lot of power there and some real challenges, especially with the data we have today. Let's start right at the beginning. What exactly is linear regression? Why is it, everywhere?
Right. So at its heart, linear regression is about trying to predict one thing. Let's call it the outcome variable, y. And we do that using a bunch of other things, characteristics, factors, covariates. We call those x. Now imagine you had infinite data, the whole population. In that perfect world, you could define the ideal prediction rule. It's called the best linear prediction, or BLP. It's basically the linear combination of x that gets closest to y, on average, minimizes the error. So this best linear prediction problem is finding that perfect linear recipe, using our x's to predict y. Whatever that recipe can't predict, the leftover bit, that's the residual or the error, epsilon. And here's the really neat part. That leftover bit, the residual, it's mathematically unrelated or orthogonal to the x's you used. It means the unexplained part has no linear relationship left with the predictors you put in.
Okay, but here's something I always wonder. It's called linear regression. How on earth can a straight line method deal with all the messy, curvy, nonlinear stuff in the real world? It just seems limited.
Oh, that's a great question. And the key is this idea of constructed regressors, or maybe better, features. Instead of just using your raw data W, you transform it. You create new variables from the original ones. Like if you have age, you could add age squared as a new feature, or age cubed. Or maybe you multiply two variables together, like years of experience times level of education, those interaction terms. So here's the insight. The prediction rule is still linear in these new fancy features you created. But because those features are nonlinear transformations of the original data, the whole thing becomes nonlinear in terms of that raw data. It lets you capture really complex curves and relationships.
Ah, okay, so linear refers to how the features are combined, not necessarily the shape of the final prediction against the original data.
Exactly. It's a subtle but super important distinction. It unlocks a lot of flexibility. And it's also important to distinguish this best linear predictor, the BLP, from the theoretical best predictor, full stop. That best predictor, let's call it GW, is the absolute best possible rule, linear or wildly nonlinear, that minimizes prediction error. Our BLP is the best linear approximation, or BLA, to that ultimate best predictor. It's the closest a linear rule using our chosen features can get.
The source has this great visual, right? Trying to approximate a smooth curve like an exponential function. If you just use a straight line, it's pretty bad, but then you add a square term, make it quadratic. Suddenly it fits much better. Add a cubed term. It's almost bang on. What really strikes you about how just adding those simple polynomial terms makes such a huge difference? It really shows the power of feature construction.
It really does. It shows how that linearity isn't as restrictive as it first sounds, if you're clever about your features. Okay, but now let's hit the reality check. We never have infinite data, right? We only have a finite sample, and that's where ordinary least squares OLS comes in. OLS is the practical method we use with our sample data to estimate that best linear prediction rule. It works by minimizing the prediction error, the squared error, in the sample we actually have. But this brings up a fundamental statistical point. We're trying to estimate, say, p different coefficients for our p features, using only n observations in our sample. For the OLS estimate from our sample to be a good approximation of the true population rule, that ratio, p divided by n, generally needs to be small.
Right, you need way more data points than things you're trying to estimate. So what happens if Pn isn't small, if you have lots of features relative to your data?
Yeah, that's where you run headfirst into overfitting.
The dreaded overfitting. Explain that.
Overfitting is when your model learns the training data too well. It doesn't just capture the underlying patterns, it starts fitting the random noise, the quirks specific to that particular sample. So it looks great on the data it was trained on, but it performs terribly when you show it new, unseen data because it hasn't learned the generalizable truth. The source gives a stark example. If p equals n, meaning you have as many features as data points, OLS can often give you a perfect fit in sample, 0 error, r squared of 1. Even if, in reality, those features have 0 predictive power for y in the wider population, the population r squared could be 0. Even if p is just half of n, the sample r squared might look like 0.5, while the true population r squared is still 0. It's misleading.
It's like memorizing the answers for one specific test, but having no clue how to solve similar problems on a different test.
Exactly like that. Perfect analogy. The model doesn't learn, it just memorized. And that's why statisticians develop things like adjusted R squared and adjusted MSE. These metrics penalize the model for having too many parameters, trying to give you a more realistic estimate of how it might perform out of sample. Sort of a built-in skepticism.
Okay, those adjusted metrics help, but how do we really know how well a model will do in the wild, especially if we suspect overfitting? What's the gold standard?
The most reliable general approach is sample splitting. It's simple but powerful. You split your data, you use one part, the training sample, to build your model, estimate those coefficients. Then you take the other part, the testing sample, which the model's never seen, and you evaluate your trained model on that data. Calculate the MSE and R squared on the test set. That gives you a much more honest picture of its true predictive power on new data. Cross-validation is a related, often more data-efficient technique that does this multiple times.
Okay, theory's great. Let's make this concrete. Apply it to that real-world example, wages. Using data from the U.S. Current Population Survey, CPS 2015, how can we use this to predict wages and look at wage gaps?
Right. So we focused on two main questions using this data, specifically for single, never-married workers. First, how well can we predict log hourly wages using job-related characteristics like education, experience, occupation, industry, region? Second, what's the predicted difference in wages between men and women who have the same measured characteristics? We built a couple of models, a basic model with 51 raw characteristics, and then a flexible model where we added more features, polynomials of experience, interactions between experience and education, things like that. This one had 246 features, so P51 versus P246.
And what happened? This is where it got interesting, Ro.
It did. On the training data, the flexible model looked a bit better. Higher adjusted R squared seemed like a better fit.
But then the test set.
Exactly. When we evaluated both models on the unseen test data, the simpler basic model actually did slightly better. Lower out-of-sample error, slightly higher out-of-sample R squared.
So adding all that complexity, those extra features, it actually hurt performance on new data. Classic overfitting, even if mild here.
Precisely. It's a perfect illustration of why you have to test out of sample. What looks good in sample might not generalize. To really hammer this home, we then tried an extra flexible model. This one had 979 features, tons of interactions. Now, P is getting quite large relative to N. And here, OLS really showed its weakness. The in-sample R squared was okay, about 0.47, but the out-of-sample R squared on the test set, it cratered to just 0.15. Huge overfitting. The model is just noise fitting.
Wow. So just throwing features at OLS can backfire badly if P gets large.
Definitely. But then we tried something else on that same extra flexible model, lasso regression. Lasso is different. It's a penalized method. It actively tries to simplify the model by shrinking coefficients, even setting some to 0 if the features aren't pulling their weight. It does automatic variable selection, in a sense.
And how did Lasso do?
Much, much better. With Lasso on the 979 feature model, the in-sample and out-of-sample R squared values were very close. It didn't suffer that massive overfitting drop-off we saw with OLS. It shows how these penalized methods are much better suited for situations where you have a lot of potential predictors relative to your data points. They handle the complexity more intelligently.
Okay, that covers prediction and overfitting, but what about the second question, understanding the source of differences, like that wage gap? We want to isolate the effect of one thing, like sex, while holding all those other factors constant, right? How do we do that cleanly?
This brings us to a really elegant idea, partialing out. It's a bit mathematical, but the intuition is straightforward. If you want the effect of, say, being female on wages after accounting for education, experience, etc., you basically do two things. First, you predict wages using only the controls, education, experience, etc. Find the part of wages explained by them. Second, you predict the female variable using those same controls. Find the part of being female that's correlated with them. Then you look at the relationship between the residuals, the part of wages the controls couldn't explain, and the part of being female the controls couldn't explain. The relationship between those two clean or residualized variables gives you the conditional effect you're after. There's a theorem, Frisch-Wall-Lovell, that proves this residual-on-residual regression gives you the exact same coefficient for female as if you just ran the big regression with all variables included. It's a way to isolate the unique contribution.
Neat. So it mathematically strips away the influence of the other factors. What did this show for the wage gap in the CPS data?
Okay, so for these never-married workers, first, the simple difference in average log wages. The unconditional gap males earn about 3.8% more than females on average. But then, we use the model, controlling for education, experience, occupation, region, industry, all that stuff. The conditional prediction told a very different story. A female worker was predicted to earn about 7% less per hour than a male worker with the exact same measured characteristics.
Wow, so after accounting for observable job factors, the gap actually points the other way, and it's larger.
Exactly. And running the parceling out regression directly, regressing residualized log wage on the residualized female indicator, gave precisely that same 0.07 coefficient. It confirms the finding. We can also decompose this using something called the Kitagawa-Oaxaca blinder method. It shows that the raw 3.8% gap favoring men is a combination of two things. Part of it is explained by differences in characteristics. In this sample, women actually had characteristics, like higher education, that should predict higher wages for them. But this effect was overwhelmed by the unexplained part that noticed 7.0% difference in pay given the same characteristics. That's the conditional gap we found.
That really highlights the difference between just comparing averages and doing a proper conditional analysis. Okay, let's push this further. What happens when things get really extreme? When P, the number of features, gets close to N, the sample size. You mentioned standard OLS theory breaks down.
It does. Let's go back to that extra flexible model with P979 features. But this time, imagine we only had N 1,000 observations. So Pn is almost 1. This is a truly high-dimensional setting. In this regime, the standard formulas we use to calculate the uncertainty of our OLS coefficients, the standard errors become unreliable.
Unreliable how?
Well, the most common type, the basic robust standard error, tends to be systematically too small. It understates the true uncertainty, making results look more precise than they are. Another type, called the jackknife or HC3, is generally better, more conservative, but it's still not technically consistent in this setting. It doesn't reliably converge to the true value.
So our confidence intervals are p-values. They could be misleading with OLS when p is large relative to n.
Correct. But here again, methods designed for high dimensions come to the rescue. We looked at double lasso for estimating the conditional effect of being female in this PAN scenario. Double lasso is specifically designed to provide reliable, statistically valid estimates in standard errors, even when P is large, potentially much larger than N. And when we compared, the OLS standard errors, even the better HC3 ones, were much larger than theory would predict if OLS was working properly. They were inflated by the high dimensionality. Double lasso's standard errors, however, behaved exactly as expected from asymptotic theory. They scaled correctly.
So the punchline is?
The punchline is that standard OLS just isn't adaptive in these high-dimensional settings. Its usual nice properties don't hold up. It really drives home that if you're working with complex data sets where you have potentially many features relative to your observations, you likely need to move beyond basic OLS. You need these more modern machine learning techniques like lasso or double lasso, not just for potentially better predictions, but also to get reliable statistical inference, trustworthy standard errors, and confidence intervals.
So quite a journey. We went from the 1800s roots of least squares through understanding prediction, the pitfalls of overfitting when Pn isn't small, the importance of sample splitting, and saw how these tools, when used carefully with things like partialing out, can help unpack complex real-world issues like the wage gap. Hopefully, getting a feel for concepts like PN ratios, feature construction, and residualization gives you, the listener, a much richer way to think about data analysis.
Absolutely. And it underscores that while linear regression is foundational, knowing its limits is just as important as knowing its strengths. Especially in high dimensions, these limitations motivate the need for more advanced ML methods to ensure we're actually drawing robust conclusions from complex data.
So here's something to chew on. If a tool as seemingly straightforward and old as linear regression has these layers of complexity, these potential traps like overfitting, and requires careful handling, What does that tell us about how critically we need to approach any claims based on data analysis, especially in our world that's just drowning in data? And what other hidden patterns, what other stories are lurking in that data, waiting for the right tools, maybe tools we're just starting to develop to bring them to light? We'll keep digging into questions like that on future deep dives.